In 1992, the passenger liner QE2 grounded on a rocky shoal south of Cuttyhunk Island, Massachusetts. Bizarrely, the rocks that she hit were around 34 feet underwater, but her draft was only 32 foot 4. So how could she possibly have hit them, let alone manage to damage in excess of 400 feet of her hull in the process? Before every voyage, ships plan their passages on a nautical chart. The idea is that you can see things like hazards, obstructions, and importantly, the depths of water. In theory, just make sure the depth is enough so that you always remain afloat. In the case of the QE2, their track took them over a sounding showing a depth of 39 feet, which seemed fine as it should have given plenty of under-keel clearance. With ships, you have the draft, which is the distance from the waterline to the bottom of the keel, so for QE2 that day it was 32 foot 4. You also have the depth of water, which is the measure from the seabed to the water's surface. That's comprised of the charted depth, so 39 feet, plus the height of tide, which was another roughly 1.5 feet. With a total depth of water of 40.5 feet and a draft of 32 foot 4, you should end up with an under-keel clearance of around 8 foot. On most ships, we're generally happy to maintain a UKC of at least 10% of the draft, so you can see why on QE2 they were quite happy with their predictions. Of course, one of the key assumptions that we've made is that you accurately know the depth of water to be able to work out your UKC. That doesn't help you if, for example, there's an uncharted shoal area shallower than the chart describes. Maybe there is a nice 39-foot sounding here obtained back in 1939 during the last survey, but they just happened to miss a large boulder field here with depths as shallow as 34 feet. This is exactly what happened to the QE2. The shoal was only found because they ran into it. But that leads us to the question and the main point of this video. How did she run aground in 34 feet of water when her draft was only 32 foot 4? Well, do you remember the video around 6 months back about the Texas chicken? I told you how ships in the narrow Houston ship channel use the physics of interaction to pass each other. In simple terms, a vessel moving ahead has a positive pressure area at its bow, a negative pressure area along the sides, and another positive area at the stern, right behind the propellers, surrounded by a negative area. In the Texas chicken, two vessels approach each other head-on until the last second when they each turn to starboard. The positive pressure areas at the bows act to initially push the bows apart. Then, the negative midship pressure and bank effect act to pull the bows straight again so that they can pass parallel. Next, when the vessels clear each other, bank effect pushes the bows back to the centre of the channel. Finally, the negative pressure between the sterns act to pull the sterns into the centre, straightening both vessels up as they complete the manoeuvre. The whole thing relies on Bernoulli's principle, which states that an increase in the speed of a fluid occurs simultaneously with a decrease in its pressure. Looking at our regular ship and the pressure points, it makes sense. From the point of view of the ship, water moves backwards. At the bow, that speed appears slower because the bow is pushing some water forwards, heaping it up. That slower speed corresponds with the increase in pressure that we talk about. Then, along the sides of the ship, water actually moves faster as all that heaped up water from the bow rushes towards the empty space at the stern. This increase in water speed generates lower pressure along the ship's sides. Finally, at the stern, we have the pressure created by the sheer volume of water moved by the propeller, but we also have the water being dragged along by the ship. This gives us the negative area where the water is sucked astern by the propeller and the positive area where it's dragged by the ship. Of course, you also have the heaping effect from the wash too, which we also simulate as a positive area. But what's all this got to do with UKC and how is it relevant for the QE2? Well, the same interactive physics applies between ships and the seabed as it does between ships and other vessels, and we call it squat. Take this vessel which is floating in open water. It's sat at equilibrium, meaning the force due to buoyancy is equal to the force due to gravity. When the vessel moves ahead, it develops all those pressure areas that we talked about before. At the bow, there is positive pressure, along the hull there is negative pressure, and right behind the ship, there is generally a negative area. The overall effect is that the ship naturally sits a little lower in the water, usually trimmed by the stern. The exact trim is determined by the shape of the vessel, as that impacts where the pressure areas are felt. Ships with finer lines, like a pointier bow or stern, will feel the average effect further aft and trimmed by the stern. Blockier ships, on the other hand, are going to tend to drag more water along with them, as their shape is less efficient in letting it flow past. This increases the positive area at the stern, meaning that they will tend to trim more evenly or even by the head. Either way, in open water it's not really that noticeable because the forces aren't that great and the ship's angle of attack kind of counters the lower pressure areas anyway. But look what happens when you bring the seabed closer to the ship. you're restricting the area through which the water under the vessel can flow, increasing its speed. Our mate Bernoulli told us that an increase in the speed of a fluid occurs simultaneously with a decrease in its pressure. With that increased force pulling the ship down, it's going to have to sit lower in the water to be able to generate enough buoyancy to find a new equilibrium. The ship is experiencing squat. The faster it goes, the greater the squat. It's approximately a squared relationship, so if you double the speed, you'll quadruple the squat. Similarly, the shallower the water, the greater the squat, as you're just restricting the space through which the water can flow. In the case of the QE2, it's estimated that her speed and the depth of water in that area meant that she could have experienced around 8 foot of squat. Suddenly, the numbers that we've been working with don't look quite so comfortable. Her 32'4" draft plus 8 feet of squat gives just over 40 feet, explaining easily how she was able to run aground on rocks that were measured around 34 foot down. Of course, squat isn't always a bad thing. By understanding it properly, you can use it to your advantage. For example, when Oasis of the Seas was built, she was too large to fit under a bridge on the river that would lead her to sea. But by running at speed, they were able to use squat to suck her closer to the seabed and make it underneath with room to spare. If you would like to hear more about the fascinating ways ships use the physics of interaction, I'd recommend you next go and check out my video on the Texas chicken. Otherwise, I'd just like to send a massive thanks to the community for helping to make this video. I know this type is unlikely to get loads of views, so your support is what makes them possible.